Hello students, in today's lecture we are going to learn about mechanical properties of fluids, NCERT section 9.2.4, and we will solve example 9.4 to 9.6. This is disclaimer. Learning objective. By the end of this lecture you will be able to understand hydraulic machine principles to solve practical problems involving force, amplification, and mechanical advantage in fluid systems. In today's lecture, we will cover first example 9.4, then 9.2.4 hydraulic machines. After that, example 9.5, and then last example 9.6. Alright, example 9.4. At a depth of 1000 meter in an ocean, what is the absolute pressure? B. What is the gauge pressure? C. Find the force on a submarine window of area 20 cm into 20 cm. If the interior is maintained at sea level atmospheric pressure. Alright. So density of sea water is equal to 1.03 into 10 raised to the power 3 kilogram per meter cube, and G is equal to 10 meter per second square. Let's see the solution. So let's start by identifying what is the given in the problem. We have a depth of 1000 meters in the ocean. Alright. Sea water density rho equal to 1.03 into 10 raised to the power 3 kilogram per meter cube, and window area A equal to 20 into 20, so it will be 400 centimeter square. Here we need to convert it centimeter square to meter square. Alright, so by dividing 100 and 2 times 100, so it will be 0.04 meter square. Alright, so acceleration due to gravity, so it will G equal to 10 meter per second square. Alright, atmospheric pressure Pa equal to 1.01 into 10 raised to the power 5 Pascal. Now let's start by determining the absolute pressure at this depth. Absolute pressure is the total pressure exerted on an object, including atmospheric pressure. So the formula for absolute pressure is P equal to Pa plus rho GH. Here Pa is the atmospheric pressure at sea level, rho is the density of the fluid, G is the acceleration due to gravity, and H is the depth. This equation helps us calculate the pressure at any given depth. So substitute the known values into the formula. So we have P equal to 1.01 into 10 raised to the power 5 plus 1.03 into 10 raised to the power 3 into 10 into 1000. Alright. So solving this, you will be get the value of P. So simplifying the equation, we get P equal to 1.01 into 10 raised to the power 5 plus 1.03 into 10 raised to the power 7. So we calculate the absolute pressure as P equal to 1.041 into 10 raised to the power 7 Pascal. As we know, 1 atm equal to 1.01 into 10 raised to the power 5 Pascal. So pressure at this depth is about 104 atmospheres. All right. Now uh, let's focus on calculating the gauge pressure. Gauge pressure is the pressure relative to atmospheric pressure. So the formula for gauge pressure is P minus PA is equal to rho GH equal to P gauge, where P is the absolute pressure, PA is the atmospheric pressure, rho is the density of the fluid, and G is the acceleration due to gravity. Alright, and H is the depth. Substituting the given values into our formula, we have Pg equal to 1.03 into 10 raised to the power 3 kilogram per meter cube into 10 meter per second square into 1000. So after performing the calculation, we find that P equal to 103 into 10 raised to the power 5 Pascal. Remember, 1 atm is approximately 1.01 into 10 raised to the power 5 Pascal. So this result shows us how many atmospheres of pressure are exerted by the water at this depth. So we can see that the gauge pressure is approximately 103 atm. This highlights the significant pressure exerted by the ocean at 1000 meters depth. Alright. Now uh, let's focus on part C uh, of the problem, which involves calculating the force on the submarine window. First, we need to determine the pressure outside the submarine. This pressure is a combination of atmospheric pressure and the pressure due to the water column above the submarine. So it will be the formula for pressure outside the submarine is P is equal to PA plus rho GH. Here PA is the atmospheric pressure, rho is the density of seawater, G is the acceleration due to gravity, and H is the depth. So pressure inside the submarine is PA. So this is important because it allows us to calculate the difference in pressure between the inside and outside, which is the gauge pressure. So the net pressure acting on the window is the gauge pressure, which is the difference between the outside pressure and the inside pressure. So this gauge pressure is what causes the force on the window. So force acting on the window is F is equal to P gauge into A. Alright. So substitute the values, we calculate the force. F equal to 1.03 into 10 raised to the power 7 into 0.04. After performing the calculation, we find that the force on the window is 4.12 into 10 raised to the power 5 Newton. Now 9.2.4 hydraulic machines. So now we are going to explore the fascinating world of hydraulic systems. Our main aim is to understand how pressure, transmission and force amplification work in these systems. This is important because hydraulic systems are used in many machines and tools that rely on fluid power to operate efficiently. Let's dive into what hydraulic machines are. So these are machinery and tools that utilize fluid power for their functioning. In hydraulic machines, a large amount of power is transferred through small tubes and hoses. This is a key feature because it allows for efficient power transmission over distances without the need for large cumbersome components. Hydraulic machines are a practical application of Pascal's law. This law states that pressure applied to a confined fluid is transmitted undiminished in all directions. Understanding this principle helps us see why hydraulic systems can effectively amplify force, making them so powerful in industrial applications. These devices use fluids to transmit and amplify forces, which is essential for many modern conveniences and industrial processes. Alright, so think about how this technology allows for the smooth operation of elevators or the precise control of robotic arms. Now, let's consider a horizontal cylinder with a piston and three vertical tubes at different points. So, as shown in figure 9.6a, three vertical tubes A, B, C. Alright. So, in this setup, the pressure within the horizontal cylinder is indicated by the height of the liquid column in the vertical tubes. Height of the liquid column. Look at here. A, B, and C. This visual representation helps us understand how pressure is distributed within the system. So it's important to note that the pressure is necessarily the same in all vertical tubes. Alright. So tube A, tube B, and tube C. Alright. Pressure is same in all vertical tubes. This uniformity is a key characteristic of fluid pressure in a closed system, demonstrating how pressure is evenly distributed. If we push the piston, look at here. If we push the piston, the fluid levels rises in all tubes A, B, C, reaching the same level in each one. Alright. This shows us that when we increase the pressure on the cylinder, alright, so it is distributed uniformly throughout the fluid and maintaining equilibrium. Alright. So here pressure on the cylinder was increased. It was distributed uniformly throughout. Now, let's start with the fundamental principle of pressure transmission in fluids. So, whenever we apply external pressure to any part of a fluid contained in a vessel, this pressure is transmitted undiminished and equally in all directions. This is a crucial concept because it explains how hydraulic systems can efficiently transfer force from one point to another. So here we have an illustration to help visualize this principle. Alright. So whenever external pressure is applied on any part of a fluid contained in a vessel, it is transmitted undiminished and equally in all directions. I think this is clear. So notice how the external pressure applied to the fluid is essentially transmitted in all directions within the vessel. Alright, this one. This uniform transmission is what allows hydraulic systems to amplify force effectively. As we look at the figure 9.6a, consider how this principle is applied in real world systems like a car brakes and hydraulic lifts. Now, let's dive into the mathematical analysis of hydraulic systems. This will help us understand the principles behind how these systems work. So consider a hydraulic system with two pistons. All right. We have a small piston within area A1. Look at figure. Area A1 and area A2. A2. All right. So larger piston area with A2. All right. So where A2 is greater than A1. So the schematic diagram illustrating the principle behind a hydraulic lift, which is a practical application of this concept. So now let's focus on the force applied to a small piston, which we call F1. All right. So F1 is force applied to a small piston. The pressure created by the force is given by the formula, and that is force is equal to F1 divided by A1. Here P is represents the pressure, F1 is the force applied, A1 is the area of the small piston. And this pressure P acts on the pressure second one. The pressure acts on the large piston, F2 equal to pressure into area, pressure into A2. So therefore F2 equal to F1 into A2 divided by A1. This equation demonstrates how the force on the larger piston is amplified compared to the force on the smaller piston. Alright. Now let's dive into the concept of mechanical advantage. So by adjusting the force applied at area A1, we can move the platform up or down. Take a look at figure 9.6b, this one, which shows a schematic diagram of a hydraulic lift. So this device is commonly used to lift heavy loads, demonstrating the practical application of hydraulic systems. So now let's focus on how the applied force is increased. So the force is amplified by the factor of A2 by A1. This means that the larger the area A2 compared to A1, the greater the force amplification. This is a key principle in hydraulic systems, allowing us to lift heavy objects with less effort. So this factor A2 by A1 is what we call the mechanical advantage of the device. It's a measure of how much the force is amplified, and it's a critical concept in understanding the efficiency of hydraulic systems. Remember, the greater the mechanical advantage, the easier it is to lift heavy loads. So formula for mechanical advantage, Ma equal to F2 by A1. F2 by F1 is equal to A2 by A1. Here Ma stands for mechanical advantage. F2 is the output force and F1 is the input force. Alright. Now let's start by discussing the conservation of volume in hydraulic systems. So here we see that for incompressible fluids, the volume displaced by the small piston equals the volume gained by the large piston. Notice the schematic diagram illustrating a hydraulic lift. This device uses the principle of volume conservation to lift heavy loads efficiently. Alright. So look at here how the pistons are connected and how the fluid moves between them. So the equation A1 L1 equal to A2 L2 represents the conservation of volume in mathematical terms. A1 and A2 are the cross-sectional areas of small and large pistons respectively, while L1 and L2 are the distances they move. This equation shows us that the product of the area and the distance moved is constant for both pistons. Therefore, by rearranging the formula, you will get L2 upon L1 is equal to A1 upon A2. So this equation tells us that the ratio of the distances moved by the pistons is inversely proportional to the ratio of their areas. This means that if the small piston moves a certain distance, the large piston will move a shorter distance. But with the greater force, this principle is what allows hydraulic systems to amplify force and perform heavy lifting tasks efficiently. 9.5. Two syringes of different cross sections without needles filled with water are connected with a tightly fitted rubber tube. Diameters of the smaller and larger pistons are 1.0 cm and 3.0 cm respectively. Find the force exerted on the larger piston when a force of 10 Newton is applied to the small piston. B. If the smaller piston is pushed in through 6 cm, how much does the larger piston move out? Let's see the solution. So let's start by identifying what we know. We have two pistons with different diameters. So first we have the diameter of the smaller piston, which is 1.0 centimeter, or in meter it will be 0.01 meter. Next, the diameter of the larger piston is 3.0 centimeter or 0.03 meters. With this information, we can calculate the area of the larger piston. So applied force on the small piston, F1 equal to 10 Newton. This force will be transmitted through the fluid to the larger piston. We will use this information to find out how much force is exerted on the larger piston. So smaller piston is pushed in by 0.6 centimeter or 0.06 meters. This movement will cause the larger piston to move out, and we will calculate exactly how much it moves. Alright. Now let's start by discussing force amplification. When a force is applied to a fluid in a confined space, it can be transmitted to another area with a different cross section, resulting in a different force. A1 equal to pi into d1 upon 2 whole square. So substituting the diameter of the smaller piston into the formula, we have A1 equal to pi into 0.01 divided by 2 whole square. So solving this, you will get A1 equal to pi into 25 into 10 raised to the power minus 6 meter square. This gives us the area of the smaller piston in square meters, which is necessary for further calculation involving force and pressure. Now let's calculate the area of the pistons. Remember, the area of a circle is given by the formula A equal to pi into d by 2 whole square, where d is the diameter. So A2 equal to pi into d by 2 whole square. So A2 equal to pi into 0.03 divided by 2 whole square after substituting the values in the formula. So performing the calculation, you will be get A2 equal to pi into 225 into 10 raised to the power minus 6 meter square. Alright. Now using Pascal's law, the formula we use here is F2 equal to A2 upon A1 into F1. This equation shows that the force on the larger piston F2 is the product of the force on the smaller piston F1 and the ratio of the areas of the pistons A2 upon A1. So now let's substitute the values into the formula. We have F2 equal to 225 into 10 raised to the power minus 6 divided by 25 into 10 raised to the power minus 6 into 10. So simplifying the equation, we find 90 Newton. This is the force exerted on the larger piston. Alright. Now let's focus on part B of the problem, which deals with the distance relationship between the pistons. So water is considered perfectly incompressible, meaning its volume does not change under pressure. The volume displaced by the smaller piston moving inward is equal to the volume displaced outward by the larger piston. This concept is based on the conservation of volume. From the conservation of volume, we derive the equation L1 into A1 equal to L2 into A2. Alright, this one. So L2 equal to A1 divided by A2 into L1. Now substituting the values of the areas and the distance moved by the smaller piston. So we have L2 equal to 25 into 10 raised to the power minus 6 divided by 225 into 10 raised to the power minus 6 into 0.06. Alright. So solving for L2. L2 equal to 1 by 9 into 0.06. So L2 equal to 0.0067 meter. So L2 equals to 0.67 centimeter. This shows the actual distance the larger piston moves out. In a car lift, compressed air exerts a force F1 on a small piston having radius 5.0 centimeter. This pressure is transmitted to a second piston of the radius 15 centimeter. If the mass of the car to be lifted is 1350 kg, calculate F1 and the necessary pressure. Alright, let's see the solution. So let's start by looking at the given information for this problem. So we see the radius of the small piston is given as 5.0 centimeter, which we convert to meters for consistency in our calculation. So it will be 0.05 meter. Radius of the larger piston R2 equal to 15 centimeter. Alright, so again we convert this to meters, so it will be 0.15 meter. The mass of the car is provided as 1350 kg. And we also have the acceleration due to gravity, which is 9.8 meter per second square. This constant is used to calculate the weight of the car. Weight of the car to be lifted, F2 equal to mg. So F2 equal to, substituting the values, you will be with 1350 into 9.8. So it will be 13230 Newton. This is the force exerted by the larger piston to lift the car. Alright. Now let's start by calculating the area of the small piston. The formula for the area of a circle A equal to pi r square. Here r is the radius of the small piston, which is 5.0 centimeter or 0.05 meters. So we have A1 equal to pi into r1 square. So just put the value of r1 and you will be get A1 equal to pi into 0.05 whole square. So it will be pi into 2.5 into 10 raised to the power minus 3 meter square. So calculate the area. So it will be A2 equal to pi into 2.25 into 10 raised to the power minus 2 meter square. Alright. Now using Pascal's law, the equation we use is F1 equal to A1 divided by A2 into F2. Here F1 is the force on the smaller piston and A1 and A2 are the areas of the small and large pistons respectively, and F2 is the force needed to lift the car. Substituting the values into the equation, we have F1 equal to 2.5 into 10 raised to the power minus 3 divided by 2.25 into 10 raised to the power minus 2 into 13230. So F1 equal to 1 by 3 into 13230. So F1 equal to 1470 Newton. Required force is F1 equal to approximately 1.5 into 10 raised to the power 3 Newton. Alright, now let's focus on the required pressure for this system. So we start the formula for pressure, which is P equal to F1 divided by A1. Here P represents pressure, F1 is the force exerted by the small piston, and A1 is the area of this small piston. This equation shows us how pressure is directly proportional to force and inversely proportional to area. So substituting the known values into the equation, we have 1470 divided by pi into 2.5 into 10 raised to the power minus 3. So after performing the calculation, we find that the pressure required as P equal to 1.9 into 10 raised to the power 5 Pascal. This result tells us the amount of pressure needed to lift the car using the given piston system. So let's convert this pressure into a more familiar unit. We find that the pressure is approximately 1.9 Newton atm. 1.9 atm. This conversion helps us relate the calculated pressure to everyday experiences like atmospheric pressure. Now let's summarize what we have learned in this lecture. We started with hydraulic machines and show how. So hydraulic machines use fluids power to transfer and amplify forces through a small tubes and hoses. They operate based on Pascal's law. Pressure applied to a fluid is transmitted equally in all directions. In a horizontal cylinder with vertical tubes, fluid levels reach the same height when pressure is applied, demonstrating uniform pressure distribution. Force amplification in hydraulic system depends on the ratio of piston areas A2 by A1. Mathematical relationship F2 equal to F1 into A2 divided by A1. And mechanical advantage Ma equal to F2 by F1 is equal to A2 by A1. For incompressible fluids, volume conversion applies A1L1 equal to A2L2. The displacement ratio is inverse to area ratio L2 by L1 equal to A1 divided by A2. This principle is widely used in modern industrial processes and machinery and like hydraulic lifts. The larger the difference between piston areas, the greater the force amplification. Now we have some practice questions. First, a hydraulic lift has pistons with areas 20 cm square into 400 cm square. If a force of 100 Newton is applied to the smaller piston, what force will be exerted by the larger piston? In a hydraulic system, what happens to the pressure when it is transmitted through the fluid? Calculate the mechanical advantage of a hydraulic system where the radius of the larger piston is 15 cm and the radius of the smaller piston is 3 cm. If the smaller piston in a hydraulic system moves down 10 cm and its area is 5 cm square, what volume of the fluid is displaced? A hydraulic lift has a mechanical advantage of 25 if the area of the smaller piston is 4 cm square. What is the area of the larger piston? Alright, so these are the practice questions. Thank you for your attention.